In the Virtual Planet Lab, fantastic worlds can be built, like a science fiction novelist with a supercomputer as a writing partner.
So we can take something that's like the Earth, but we whip away the sun, and we replace it with a star of different size and temperature. So what we've done with the Virtual Planetary Laboratory is modeled planets that started out as Earth-like and put them around stars that were much hotter, with much stronger UV radiation, for example, than our own sun.
The models can produce bizarre alternate Earths, filled with plants that are bright red, orange, or even pitch black. Photosynthesis can vary greatly depending on the light of the star that's shining on it.
Planets around F-stars, for example, where the light from the star is much bluer, the plants there will tend to absorb more blue light, and so those plants could potentially be more likely to reflect red, orange, and yellow light, and so will appear red, orange, and yellow to us.
Plants on a world around weaker stars could evolve their coloration to use every bit of energy falling on them.
If you go down to much cooler stars than our sun, to M stars, plants on planets around M stars might in fact be black because they want to absorb as much light as possible to do their photosynthesis and to feed.
And then there's the water world planet, a theoretical Earth circling a volatile M-type star that constantly hits the planet with outbursts of deadly radiation.
And how does life cope on the surface of that planet? Is it possible to have life even when you have a flaring M star? And it turns out that you can actually live about 9 meters underwater on a planet around an M star and still escape the worst of the flares, but still have enough light to be able to do photosynthesis and to survive.
Everything looks good from here.
And as future exploration missions are being drawn up, many scientists are focusing on what it would take to detect the byproducts of life on a distant planet.
Life produces gases. Life stinks. You can smell it. And we're going to look for those gases with these high-resolution spectrometers.
So what we really need to do is take the light from another Earth-like planet and analyze it to find out what the chemical composition of that atmosphere is.
Finding the locations of planets is something that UC Berkeley astronomer Jeff Marcy is very good at. He and his astronomy colleague, Paul Butler, are credited with finding more exoplanets than anyone else.
A planet that's farther from its host star will be very cool. And so there's a domain in between that we sometimes call the Goldilocks zone or the habitable zone, where the temperature is just right. And by just right, I mean lukewarm, so that water would be in liquid form. And of course, it's liquid water that's the prerequisite for life.
When we look at other planets and we ask, could there be life on other planets? My first question is, could that planet support liquid water? Yes, I'm interested. No, I'm not interested. It all comes down to show me the water.
Water is an amazing substance. We are frankly fortunate that the universe has something called water. It's the great cosmic cocktail mixer. Water is the critical stuff that allows the chemical reactions to take place that eventually lead to life.
But this special zone, where liquid water can exist, varies from place to place. If a star is a hot O type, the zone will be farther out from a sun. If it's a cool M type, the zone will be closer in. And it even changes with time. Stars are not stable. Even our own comfy habitable zone here on Earth will change in a few million years when our sun grows older and much hotter. Current technology doesn't exist to take pictures of distant exoplanets. So astronomers use the solar system star as a sort of proxy for a planet, since both were formed from the same planetary disk of material.
How do we know what a star is made out of? we don't go there and sample it, your experiment would melt.
Astronomer Wes Traub heads up the effort by NASA's Jet Propulsion Laboratory to come up with the next generation of instruments that will look at planets outside our solar system.
What we do is we just simply look at it and we break the light up into different colors. This was done several hundred years ago by Newton. He discovered that if you put a prism in a ray of sunlight, it breaks it up into blue, green, red. And you look at these different colors and you discover something very startling all of a sudden. There are parts where colors are missing, and these missing colors are a fingerprint of the constituent of the sun that you're looking at.
With current technology, we can't directly view a spectrum of a planet outside our solar system. But eventually, more powerful instruments will allow us to use the same technique to fingerprint a planet for evidence of life.
If we look at that light from the planet and break it up with a prism or something similar, we can tell what the planet is made out of, and that's how we know whether our planet has oxygen, like our atmosphere, whether it has water vapor in the atmosphere, whether it has ozone, carbon dioxide, and nitrous oxide.
But nothing in the universe stays the same over time.
When our Earth formed 4.5 billion years ago, it had a very different atmosphere than it has now.
It's a challenge that Meadows and her team anticipate as they build their models of other Earth-like planets.
We would be very short-sighted to look just for an oxygen-rich planet at the same stage of development. So the thing is, when we go out to look for habitable worlds, they could all be extremely different. They could be very diverse.
And if we find another Earth, what are the chances we'll find a civilization on it that we can communicate with? What's the number of intelligent civilizations that might exist on other Earths in the universe? What would have to go into such a calculation?
How many stars are there? How many of those stars have planets? How many of those planets are close enough to have water? And on and on.
That's a problem that astronomers Carl Sagan and Frank Drake took on decades ago. Drake came up with an equation that estimated that up to 1 million civilizations may exist in just our Milky Way alone.
The Drake equation is this series of numbers that are trying to be put together in such a way to give us a kind of way of even closely estimating how many other intelligent civilizations are out there.
Peter Ward, a professor of biology and geology at Seattle's University of Washington, thinks the Drake equation greatly overestimates the number of advanced civilizations that could exist on other Earths in the universe. Ward and astronomy professor Don Brownlee's book, Rare Earth, explains why they think complex life, animal life like humans, may be rare in the universe.
We began to think that it was just too simplistic, that there's other stuff involved.
Ward cites a number of factors that he thinks would lower the original Drake estimates of how much complex life could exist in the Milky Way, and by extension, the universe.
First of all, plate tectonics. Plate tectonics is continental drift, and one wonders why would that have anything to do with the frequency of life on the planet? Plate tectonics also produces a recycling of elements, and that recycling does some very fundamental things. The most fundamental thing it does, it produces a temperature gauge. It's like a thermostat on the planet. If we get too warm, plate tectonic processes help us cool off.
Then there's the presence of metal on the planet.
Secondly, if you want to be an intelligent civilization, you better have metal. Metal's hard to find on a planet like Mars or Venus. But plate tectonics rotates everything, causes cracks, up come the heavy metals. What else do we need? We need a good Jupiter.
Having a gas giant like Jupiter, with its strong gravitational pull in the outer reaches of a solar system, protects the inner planets, those potential Earths, from frequent catastrophic impacts.
And the reason is those Jupiters sweep up gravitationally the asteroids and the comets, flinging them away, allowing the Earth to survive without so many impacts by that debris. And so it's those protective Jupiters that allow life to proceed without impacts by these asteroids and comets that would cause mass extinctions, as indeed happened to the dinosaurs.
65 million years ago, an asteroid hit Earth and wiped out most of the dinosaurs on the planet.
Those dinosaurs went out because Jupiter failed on the job and should have been fired. Bad Jupiter that day. It let one of these asteroids sweep by, but we've seen what it usually does. Comet Shoemaker-Levy that smashed into Jupiter at the last part of the last century. That's what Jupiter generally does. So good Jupiters are good things to have, and you can make equations for this.
When considering the habitability of planets, most astronomers place great emphasis on finding worlds in the habitable zone around a star. But Ward and his co-author believe that a planet's position within the larger galaxy is also critical.
So that's why we have defined, or did define, something we call the galactic habitable zone. That area within a galaxy, not too close, not too far. It's a Goldilocks area within our galaxy that's just right.
They came up with 9 factors that make up a so-called galactic habitable zone. Earth's position in the galaxy is considered. Away from killer neutron stars, black holes, and deadly gamma ray bursts. They included the percentage of stars that have planets and the percentage that have microbial life. They even estimated how often planets might have all their life extinguished. Earth itself may have narrowly missed such an event in 1998. Then, a high-density star called a magnetar burped out a flare of deadly gamma rays, unleashing as much energy in 0.2 of a second as the sun will put out in the next 100,000 years. Luckily, the magnetar was located 20,000 light-years away from Earth.
A really good question would be to ask, what would have happened had that magnetar that burped not been 20,000 light-years away, but 10,000 light-years away? Could there be a case where we had something within a few hundred light-years? If that were the case, new calculations suggest it could punch our atmosphere off, woof, in one burst. And you go, I can't breathe. Now that's catastrophic, and that is totally possible.
Humans may be just a cosmic fluke in the universe. The optimistic assumptions of the Drake equation may just not hold up with what astronomers have learned in the past decades.
The Drake equation was a fantastic construct, but it was done in the 1960s. We know so much more now. So we've added in stuff that wasn't known then. And I think it makes it more accurate, but ultimately it also brings down the numbers. And the million civilizations I do not think can be supported by current understanding.
So how many other Earths supporting advanced civilizations does he think may exist in our Milky Way?
I've been asked over and over to make a prediction, and I'd say, well, we know it's at least one. It's more than one, I think. But I think it's more than one, but way less than a million.
Locating another civilization may happen as astronomers concentrate on looking for other Earth-like planets. But finding those Earths in the first place is a huge technical challenge for scientists. Unlike the stars that have been cataloged, planets can't be seen using current technology. A planet, when examined from light years away, is almost on top of its sun as viewed from outside our solar system. And to make matters worse, an Earth-like planet, even one many times larger than our Earth, reflects only an infinitesimal amount of light compared to its star.
So here we have a bright star and a planet which is 10 billion times fainter. It's hard to imagine what 10 billion times really is, but the way many of us think of this is, suppose you have a firefly, a very small firefly, a very weak light, and suppose that firefly is orbiting around or flying around a lighthouse. And suppose you're trying to look at this firefly flying around this lighthouse from 3,000 miles away. That's something what it's like.
Let's assume you could find that speck of a firefly from across the country, and then you had to figure out what that firefly is breathing by analyzing the gas it's exhaling. That's the challenge that faces an astronomer who first has to find a planet, then figure out how Earth-like its atmosphere is. But astronomers have figured out indirect ways to find extrasolar planets.
If that were the star, and very bright, and this were the planet, and it moved in front of that star, the star would get dimmer, and you would notice that.
It's called the transit method of discovering a planet, since it depends on seeing the travel or transit of a planet across a distant star.
The amount of light it blocks when it's in front tells us how big the planet is. So we use that to understand whether it's a small planet like Mercury, a planet like the Earth, or a huge giant like that of Jupiter. And we use the orbital period and the temperature of the star to tell us if it's in the habitable zone.
The orbital period is how long a planet takes to go around its star.
Then we'd go on its way and come back again a year later and do it over again.
When that period is combined with the type and size of the star, the information will tell scientists if the planets that are found are potentially in a habitable zone. The transit method works if the observer or the telescope is in the same plane as the star and its planets. But if you're above or below the system, another technique called the radial velocity method might be used. That method depends on careful observations of a distant star to watch if it's being gravitationally tugged back and forth by an unseen exoplanet. Astronomers can use that information to figure out details about the exoplanet that's influencing the star. Equipped with these tools, astronomers are finding hundreds of planets, some never dreamed of in astronomy textbooks. Super Earths, hot Jupiters, and even some close cousins to our own Earth. In the search for other Earths in the billions of stars in the universe, astronomers have found a relationship between the composition of a star and the probability that it may have planets, both Earth-like and otherwise.
The stars that have heavier elements in them, the iron and the nickel and the silicon, have heavier elements for a good reason. Those stars formed out of molecular clouds in the Milky Way galaxy that collapsed down to form the star, and in so doing, left some placental material around them that eventually coagulated into the planets. So it makes sense that stars that formed with lots of heavy elements will form planets that also have lots of heavier elements.
Astronomers call the proportion of heavy elements in a star its metallicity. But that doesn't necessarily mean it has a lot of metal in the conventional sense.
Metal, for an astronomer, is any element that's heavier than hydrogen or helium. So in astronomer speak, lithium is a metal, sulfur is a metal, chlorine is a metal, and not just elements like iron, gold, and silver.
An Earth-like exoplanet not only needs heavy elements in its composition and to be in a star's habitable zone, it also needs to be the right size to sustain life. Right size means it can hold on to its atmosphere and have plate tectonics and volcanoes, both considered critical to regulating a planet's temperature. To do all this, Astronomers estimate that the smallest a planet can be is 1/3 of Earth's mass. On the high side, a habitable planet cannot be greater than 10 times our Earth's mass. The very existence of exoplanets has gone from theory to reality only in the last decade.
A little over 10 years ago, we had no known extrasolar planets at all. The only planets we knew of were those orbiting our sun. And now we know of planets orbiting other stars. And of course, what's really exciting about these planets is that some of them may be habitable, and so there's a chance that there's life on some of them.
Of the hundreds of exoplanets found, some may not follow the familiar blueprint of planets in our solar system.
We found these bizarre Jupiters that orbit very close to their star. They're blowtorched hot, and these Jupiters undoubtedly got close to their star by migrating inward.
Sometimes the formation of a Jupiter-mass planet can be kind of a death knell for terrestrial planets in the system.
And what if we had been unlucky enough to have such a Jupiter in our solar system?
It would have slingshot the Earth right out of its orbit into the vast, cold darkness of outer space, and the Earth would eventually die off as a cold, dark hulk.
Over 300 exoplanets have been discovered, and more are being found all the time. But the majority are monstrously huge gas giants that hold little promise of being truly Earth-like. In the Pegasus constellation, some 50 light-years from Earth, the planet 51 Pegasi b can be found. It was the first planet discovered outside our solar system. A gas giant as big as Jupiter, but orbiting much closer to its star. It races around its sun in just 4 days. The planet 70 Virginis b is even farther away than Pegasi, at 60 light-years. It's 7.5 times as massive as our Jupiter. At first, it was believed to be in the habitable zone of the star, so it was nicknamed Goldilocks. Later calculations showed that it had an eccentric orbit that brought it to within 27 million miles of its sun, which is roasting hot, so it's no longer considered to be in a habitable range. The massive gas giant Trace 4 is over 1.5 times the diameter of our Jupiter, making it the largest planet found so far. It's 1,400 light-years from Earth. This gas giant, even though it's much larger than Jupiter, only has a little over 3/4 of its mass. It's a hot Jupiter, zooming around its sun in only 3.5 days. Astronomers haven't been able to find true Earth-like planets outside our solar system because they've not yet been able to detect such relatively small rocky planets as our Earth. The technology is just not there yet. But astronomers are having more luck finding what are termed super-Earths.
People actually being able to discover planets that could potentially be in the habitable zone around other stars. And one classic example of this is a planet called Gliese 581c.
The Gliese 581 system is located about 20.5 light-years from Earth in the Libra constellation. Gliese 581c has 5 times the mass of our Earth. There were hopes that 581c would be the first Earth-like planet found in the habitable zone of a star, but that turned out to be wrong.
Probably it's a little bit on the wrong side of the fence. So that one, instead of being a super-Earth, is probably a super-Venus.
It's like our own Venus, way on the hot side, with possible 600-degree temperatures, but also more massive than Venus. But Gliese 581c has a relative a little farther out and cooler. It's named Gliese 581d.
And this one is at the far back end of the habitable zone. where it's quite cold. When you initially look at it, you think, well, maybe that's a bit too cold. But it turns out that if the planet potentially has enough greenhouse gases, it might be possible to make that planet warm.
Another promising Earth-like planet may be HD 69830d. This is a big planet, 17 times the size of our Earth. It's about 42 light-years away from our solar system in the constellation Puppis.
HD 69830d is a potential planet where life could form because it has approximately the right temperature.
The planet could have a temperature between that of Venus and Earth, and it has a close to circular orbit, meaning it won't get toasted by close encounters with the star it's orbiting.
So you can have liquid water. The mass of the planet is maybe not so good. It's about 17 times the mass of the Earth, which could be a solid ball of rock, or it could also be a gas ball like Neptune in our solar system.
When NASA's able to fly future planet-finding missions, it's expected that astronomers will be able to get a spectrum that will give us much more information about the composition of the planet. They may be able to figure out if the planet has a solid surface, or that it's a water world, or perhaps something else entirely. The search for other Earths has taken astronomers light years from our neighborhood in space. But could another Earth exist in our own solar system? While astronomers look at star systems many light years away in hopes of finding another blue marble of a planet, other Earths may be a lot closer than that.
So imagine going back 3.5 billion years ago and visiting our solar system. You'd have seen 2 blue marbles here. Earth, water, thick carbon dioxide atmosphere, warm conditions, life. Now imagine moving a little over, you see Mars. Water on the surface, thick carbon dioxide atmosphere, warm conditions, possibly life. Well, the 2 planets start evolving. Earth stays habitable. Mars doesn't.
Both Venus and Mars are just on the edge of the Goldilocks zone of habitability. Both may be cases of failed Earths. Once you fall off that path, you may never be able to come back.
Mars is a lesson for what you need to maintain habitability for a long time. And the answer, we think, turns out to be big. You have to be as big as the Earth to maintain habitability for a long time. Mars is too small. Being too small, it has no way to recycle its elements and has no way to hold on to its atmosphere for a long time. So size matters.
And while Mars is now too cold, Venus, our other would-be Earth, has the opposite problem. It's too hot.
It was a little bit too close to its star, too close to the sun. It got hot and it stayed hot. And so all the carbon dioxide, the CO2 and so on, that formed on Earth, formed also on Venus. But on Earth, it was incorporated into rocks. On Venus, it stayed in the atmosphere. And the atmosphere basically is global warming to the nth degree. Sunlight comes in and it just doesn't leave. That planet is like the inside of a pizza oven.
Venus failed because it was born in the wrong place. Mars failed because it was born the wrong size. So we have an interesting story here, Venus, Earth, and Mars. Venus is in the wrong place, Mars is the wrong size, Earth is the right place and the right size.
So if the planets in our solar system aren't great candidates for being Earth-like, our closest galactic neighbor, Alpha Centauri, may harbor an Earth-like planet. At a little over 4 light-years away, in galactic terms, it's next door.
I think that there's a good chance that Earth-like planets are orbiting around either one or both stars in the Alpha Centauri system.
Astronomer Greg Laughlin has done computer modeling to show that Earth-like planets should exist in the system.
There's a number of reasons why Alpha Centauri is the best star in the sky for hunting for Earths. Alpha Centauri is very close by. Alpha Centauri has 2 sun-like stars. Alpha Centauri has a large quantity of the kinds of heavy elements that go into building planets.
How close is the Alpha Centauri system to us? First imagine shrinking our sun down to the size of a grain of sand.
A grain of sand is just about the smallest object that you can see with your eyes and just about the smallest object that you can actually feel with your fingers. And at the scale where the sun is the size of a grain of sand, the Alpha Centauri system is 3 more sand grains placed about 5 miles away. Now, if we wanted to get a similarly good system to Alpha Centauri, we'd have to actually go all the way over the horizon to find another stellar system that's good.
And it turns out that the stars of the Alpha Centauri system should have plenty of raw materials to make planets out of.
Alpha Centauri has a higher metallicity than our own sun does, and that implies that planet formation was a process that took place relatively easily in that system.
And last but not least, Alpha Centauri's 2 main stars provide an additional benefit.
The initial indications show that there are no Jupiter-mass planets in the Alpha Centauri system. That makes it more straightforward for terrestrial planets to form around either or both of the stars.
That's because large gas giants form around cores of ice that are as big as our entire Earth. So these giants need a lot of cold space to form these cores. Think of how far out Jupiter is from our Sun. However, when you have 2 stars with overlapping orbits in a system like Alpha Centauri, there isn't a space in the system that's big enough and cold enough to allow the formation of these gas giants.
So we expect that the planets that exist in the Alpha Centauri system, if they're there, they're terrestrial planets like the Earth or Mars or Venus. They're not gas giant planets like Jupiter or Saturn.
What if we could actually survey how many Earths are in our part of the universe? What if we could peer directly into the atmosphere of another Earth that was light years away? In order to find another Earth, astronomers have to eventually overcome the huge technical challenges of how to view a distant planet. It's a problem that NASA has tackled much like the race for the moon, with plans that stretch out over decades. The first exoplanet finding mission will be Kepler, which launches in 2009. The NASA survey project is named after the 17th century astronomer Johannes Kepler, who discovered the laws of planetary motion.
What Kepler will do is so utterly simple and yet extraordinarily powerful, it brings tears to my eyes. What Kepler will do is simply be a space-borne telescope and stare at the constellations Cygnus and Lyra, taking picture after picture after picture, with the goal of looking for stars that dim when an Earth-like planet blocks some of the starlight. And it will be the first time that we humans detect other Earth-like planets around other stars.
The principal investigator for Kepler is William Barucki. He's been championing the mission for 25 years.
Kepler basically is a space mission that puts up a very large telescope. It's very much like a camcorder. It's always taking pictures of these stars, sending that information back to you.
The mission is a comparatively small survey project to look at a fixed portion of the sky for an initial time of 3.5 years.
The main result from Kepler will be to give us a statistical count. It's a head count of what the population is. You know, how many small planets do you have and how many large planets do you have?
Kepler's results will in turn be used to help decide what will be built for the next generation of planet-finding missions.
Kepler really is one step along the way. It's to try to find Earths and find out whether they're frequent. If they are frequent, they must be close. So we can build a modest instrument. If we don't find many Earths, what that means is before you're going to find another one, you're going to have to look at a huge distance into space. So you're going to have to build a much bigger, much more expensive instrument.
The most majestic, spectacular telescope ever conceived by humanity is something called the Terrestrial Planet Finder. It will be an enormous telescope in space, frankly probably costing several $1 billion, but what it will do is absolutely unique. It will be the first telescope to take pictures of other Earth-like planets.
To directly view a planet outside our solar system, a whole new telescope technology is being developed.
To construct the Terrestrial Planet Finder that will image Earths against the glare of their host stars, we need some entirely new optical technology, a technology that frankly we haven't invented yet. The frustration is just palpable that we actually know vaguely how to detect other Earths, but we don't know exactly how to build the optics to do so.
NASA envisions the Terrestrial Planet Finder as a suite of two very different but complementary advanced concept telescopes. The first, the Visible Light Coronagraph, consists of a large optical telescope with a mirror at least 100 times more precise than the Hubble Space Telescope.
A coronagraph is a single telescope which collects the light from a star and focuses the light at the back end like a normal telescope. Except at that point, we block the light from the star and we try to let the light from the planet come through. By doing this, you cancel out the scattered light in the instrument, and so you allow yourself to be able to look at this planet which is 10 billion times fainter than the main star.
The second Terrestrial Planet Finder mission will be an interferometer.
An interferometer works by taking the light from a star that comes in and capturing it with two telescopes, sometimes more. And this combined light can be arranged in such a way that the light from the star disappears. That's good in the sense that you now can look at the planet that's next to it, and the light from the planet does not disappear. That's the magic of an interferometer.
To get all this done, new levels of precision in control and command technologies need to be perfected. Something that could take years to develop. The quest for the Holy Grail of astronomy, another Earth outside our solar system, has pushed scientists to speculate about how such a discovery could affect us.
I think if we find another Earth out there, that's going to have an enormous impact on society. I think to know that we are not alone, that we are one of many potential sites for life, I think will cause a huge paradigm shift in people's thinking.
But there's also the possibility that we may be unique in the universe, and that we may well find Earth-like planets, but no intelligent beings on them.
We have to remember something a little sobering. It is still possible that we humans are some fluke on the evolutionary tree, a twig, if you will, that happened on the East African savanna 2 million years ago, and those hominids somehow occupied a very rare niche that hadn't happened in 4.5 billion years on the Earth.
Scientists explore how our planet first formed from the dust of the solar system. how molten rock solidified to land, how our oceans filled with water, and how life arrived on Earth. These are the earliest chapters in the incredible story of how the Earth was made. When it comes to finding clues to the birth of the Earth, our planet has been good at covering its tracks. Billions of years of erosion, volcanic activity, and the shifting of continents and oceans have destroyed almost all the evidence of the earliest stages in Earth's formation. For geologists trying to discover how and when the Earth first formed, this is a major challenge.
As geologists began to question the age of the Earth, and of course they looked for older and older rocks, what we began to find was that the further back you go in Earth history, the harder it is to find any of those rocks.
The search for the oldest rocks on Earth brings investigators to the harsh desert landscape of northern Arizona. This giant hole in the ground is Meteor Crater, formed when a massive meteorite slammed into the Earth.
We didn't really have rocks from the very beginning. Well, where could we find something? What about the meteorites that have been out in space and fall on the Earth?
It was here that geologists made a vital discovery. Meteorites are older than any rocks on Earth. They had found the key that would unlock the secret of Earth's formation. If the oldest rocks came from space, that is where the investigation must begin, in space. Our solar system, 4.5 billion years ago. At its center, the young sun.
The theory that emerged was that the sun was surrounded by a cloud of dust and gas, and as that cloud cooled, little grains of minerals formed. So all these little grains of minerals floating in this gaseous cloud are moving around the sun, and they start to bump into each other.
But there was a problem with this theory. Nobody could explain how colliding microscopic mineral grains could ever create an object the size of a planet. Then, in 2003, an experiment on board the International Space Station accidentally provided extraordinary new evidence. Astronaut Don Pettit wanted to see what happened to different substances in the zero-gravity conditions of space. He did a simple experiment by pouring some salt into a plastic bag and shaking it. The results were astounding. The particles immediately began to stick to each other, forming little clumps, all held together by tiny static electric charges. Scientists realized that if grains of salt stuck together in space, then so could the mineral grains in the solar dust cloud. Here was real evidence for the fundamental mechanism that kick-started the formation of the Earth. As mineral grains in the solar dust cloud bumped into each other and stuck together, they grew into small pieces of rock orbiting the sun. Over the next few million years, some of them collided and grew bigger. Many of these rocks are still orbiting the sun today. They have drifted for the past 4.5 billion years, unchanged from when they first formed. Occasionally, they fall to Earth, and we call them meteorites. They provide scientists with an incredible window onto the past.
We brought what's called a stony type of meteorite. What the scientists do then is slice across it and look on the inside. And to a planetary mineralogist, you start seeing all kinds of wonderful things.
This meteorite contains minerals and metals from every part of the solar dust cloud.
So what we're looking at is the assemblage of all these little ancient materials that were floating around the sun in the nebula of dust and gas. And when they hit each other, they gradually aggregated into solid bodies, which got bigger and bigger.
Gradually, billions of these rocks grew as they orbited the sun. First to the size of boulders, then as big as houses. And they kept on growing. When an object reached about half a mile across, its own gravitational pull became strong enough to draw other objects towards it.
Some object in this huge number of objects going around the sun, one of them had to be the biggest. And as soon as it gets bigger than the others, it's sweeping up more objects, just like you're driving through a cloud of mosquitoes at night in your car and the front windshield's getting hit more often. So the bigger it is, the faster it grows. And the faster it grows, the more gravity it gets, and that pulls in more objects. So the biggest object starts to run away from the crowd. It starts to grow fastest.
Below the surface, Earth is separated into distinct layers. A thin crust, then a massive dense layer of rock called the mantle, and at the center, an iron and nickel core. Some extraordinary event must have occurred to transform the interior of the young planet. Geologists now believe that soon after it formed, the Earth completely melted.
Originally, the Earth was probably just a big collection of rocks like this, but it heated up to the point where these rocks all melted. And when that happened, the denser elements sank down through to the very core of the Earth, and the lighter elements floated at the top.
The huge gravitational pull dragged the heavy iron and nickel down to form the core and separated the rest of the planet into layers. What caused such a huge mass of rock and metal to heat up in the freezing depths of space puzzled geologists for many years.
We think it's from the incorporation of very hot radioactive elements. They're out there floating in space. As the Earth accretes, it includes some of this ferociously hot material. As it gets inside there, it begins to heat up the rocks around it. And if you build the Earth fast enough and you incorporate enough of this really hot radioactive elements, it'll be enough to melt the Earth from the inside out.
Only 30 million years after it began to form, Earth had become a giant round ball of boiling liquid rock and metal orbiting the sun.
Imagine a totally molten world. I mean, it had molten magma oceans, no dry land anywhere, no water, just flowing lava everywhere.
The temperature of the molten Earth was now a staggering 2,000 degrees. But at the edge of the planet, the vacuum of space is a constant minus 450 degrees, almost 2,500 degrees colder. The surface rock could not stay molten for long.
It's cooling from the outside in, so from the outside begins to crust over, and you get this little scab, like on a wound, of cooled rock, but still really hot, and then gradually begins to cool from the outside in.
In less than 1 million years, Earth's surface was covered in a thin crust. But volcanoes still spewed out lava and choking gases. Meteorites rained down in a constant bombardment. Earth had a long way to go before it could support continents, oceans, and life. Scientists investigating the earliest origins of the Earth have uncovered evidence from salt grains in space. They revealed that the Earth began to form when fragments of the solar dust clouds stuck together. The Earth's internal layers provide the clue that soon after it formed, the young planet completely melted. Scientists had worked out how the Earth first formed from a cloud of dust in space, but they were missing a vital piece of the puzzle. They still did not know the age of the Earth. Billions of years before humans evolved, Tiny mineral grains in space clumped together to form the molten ball that became the Earth. But exactly when that happened is a question that has taxed the minds of scholars and scientists for centuries. In 1650, the Irish Archbishop James Ussher added up the ages of all the prophets and kings in the Bible. His calculations led him to very precise conclusions: that Earth was created at nightfall before Sunday, October 23rd, 4004 BC. A century later, geologists realized that Earth's thick layers of sediments and volcanic lavas must have been laid down over millions, rather than thousands of years. The next breakthrough came in 1897, when physicist Ernest Rutherford figured out that measuring radioactive decay could accurately date the age of rocks. Rock samples from around the globe were found to be not just millions, but billions of years old. But in their hunt for the age of the Earth, scientists hit a major obstacle. Rocks from the earliest stages in Earth history are very hard to find.
If you want to go back as a geologist and try to find evidence of those early days, it's very hard to do on the Earth because, of course, we have rain eroding, we have tectonics and continental drift destroying continental surfaces. We simply can't find the rocks that go back to that age.
In the early 1950s, the American geologist C.C. Patterson tried a new approach, using meteorites. He knew that meteorites must have clumped together from the same mineral grains in space that formed the Earth. And that happened at the same time as the Earth was born. So if he could date a meteorite, he should get the true age of the Earth. In 1953, Patterson came to Meteor Crater in Arizona, looking for samples. The meteorite which blasted out this enormous crater was about 50 yards across. It slammed into the Earth at a fantastic speed.
Objects hitting the Earth from space may typically come in at 10 or 15 miles per second, hitting the ground, penetrating into the ground, generating an enormous pressure and shock wave and creating a huge explosion.
The meteorite hit the Earth with the force of a 2-megaton atomic bomb. The explosion vaporized most of the meteorite, but individual fragments survived.
This is one of the pieces of the object that crashed into the Earth and made this crater. This is pure iron. We know it's iron because, for example, it's magnetic. An amazing piece of something that was floating in space. This was the kind of place that people could get samples for the first radiometric dating of meteorites. And so Patterson came here and got samples like this.
Patterson dated the samples and was amazed by the results. The meteorite was a staggering 4.5 billion years old, meaning that the Earth was also born 4.5 billion years ago. Patterson had solved the problem that had defeated scientists for centuries.
There's this apocryphal story that Patterson got so excited about the date that was coming back from the laboratory and so hyper about it, he thought he was having a heart attack. And he was driven to the hospital, and it turned out to be just his excitement over this fantastic discovery.
Modern radiometric dating techniques have refined the age of the Earth to a remarkable degree of accuracy. The most recent study dates the Earth as 4,567,000,000 years old. So scientists now knew how and when the Earth was formed, but nobody had figured out what happened next. Then in 1974, a radical new theory emerged. In the early solar system, there were dozens of mini-planets chaotically orbiting the Sun. According to the theory, one of these was on a collision course with Earth. The idea was the brainchild of Bill Hartman, who was trying to explain the origin not of the Earth, but of the moon.
What we came up with was that maybe during that period of intense impacts, maybe very large impact hit the Earth and blew some crustal outer mantle rock off of the Earth into space around the Earth, and the moon formed from that material.
Hartman suggested that another planet, about the size of Mars, crashed into the Earth. He claimed that the moon could have been formed by debris from that collision. To many scientists, this was nothing but fantasy, but Hartman had evidence. Collected from the moon itself.
I fall in the plum crater getting this rock.
Footage from the Apollo 16 mission in April 1972 shows astronaut Charles Duke struggling to pick up a large sample of moon rock to bring back to Earth for geologists to analyze.
That's 20 pounds of rock.
At the Johnson Space Center in Houston, this actual piece of moon rock is still kept under strict laboratory conditions.
I would say, behold the moon. This is an actual piece of the moon, and it's the largest single rock that they brought back from the surface of the moon when the Apollo astronauts went there. We can't touch it. They don't want human beings touching these rocks and leaving organic material on them.
Until the late 1960s, geologists thought that the moon formed in the same way as the Earth, by clumps of mineral grains sticking together in the solar dust cloud. They believed it had layers, like the Earth, and a heavy iron core. But when geologists analyzed lunar samples, they were astonished to discover that the moon rocks contained much less iron than they expected.
One of the mysteries has always been, why isn't there as much iron in the moon as there is on the Earth if the two objects are right close together in space?
The question bothered Hartman so much that he began to think that conventional theories about how the moon formed might be wrong.
That lack of iron in the moon, or to put it another way, the fact that the moon is made out of rock that looks like the crust and the upper mantle material of the Earth, that was a clue that the moon may have formed from rocks from the outer portion of the Earth.
This was the key to Hartman's idea of a collision between Earth and another planet. The force of the impact completely destroyed the other planet and flung billions of tons of Earth's crust and mantle out into space and into orbit around the Earth. Within a few thousand years, this debris clumped together to form the moon. Advanced computer models show that the collision was a glancing blow. The other planet did not hit Earth head-on. This meant that while Earth's outer layers were ripped off, none of its iron core was blasted away.
That lack of iron would end up explaining why we have a moon that is only the rocky material without the iron material.
Hartman's collision idea is now accepted as fact. It was his fascination with the moon that led to a new understanding about a vital stage in the formation of the Earth.
The moon always, to me, is a reminder that we live in a larger environment than just the Earth. It's the cosmic environment. The inner solar system is our environment that we can move around in now.
In the quest to discover the age of the Earth, evidence from radiometric dating of meteorites proves that the Earth was formed just over 4.5 billion years ago. The lack of iron in rocks brought back from the moon is evidence that the Earth survived a massive collision with another planet. But vital parts of the modern Earth were still missing from the newly born planet. The investigation now needs to figure out how the Earth gained two essential components: solid land and water. $4.5 billion years ago, Earth formed out of the solar dust cloud, then survived a devastating impact with another planet. The investigation now moves 200 million years forward in time as scientists try to discover how the first continents and oceans formed. They are looking for evidence on the northeast shores of Hudson Bay, Canada. This is the desolate landscape of Porpoise Cove, the site of an important new scientific discovery. And it's all down to a young PhD student's fascination with ancient rocks.
I was interested in studying the early Earth, so the idea is to get as far as we can back in time to get these old rocks and study rocks that were there in the past.
Geologists already knew that rocks in this part of northern Canada are extremely old. But something about a small area in this vast wilderness caught O'Neill's eye.
The overall aspect of the rocks really looked different. And right away we knew that something was really bizarre, really unusual about these rocks.
The rocks are highly altered, deformed volcanic lavas known as amphibolites.
The chemistry was unusual, the mineralogy was unusual, and nobody had seen rocks like that before.
O'Neill decided the rocks needed further investigation. He sent samples to be radiometrically dated. The results were astounding.
We were in the lab in Washington, D.C. when we first got the first number out of the machine, and the first reaction is we didn't believe it. So what you do is you reanalyze the rock a second time, and then the same number comes up, and then a third time, and then again and again. So you say, okay, we'll analyze more of these rocks because I can't believe it. And these numbers, the signature, this really, really old signature keep coming up, keep coming up, and keep coming up. And in the end, you have to come to the conclusion that these rocks have been formed nearly 4.3 billion years ago.
The results were indisputable. The amphibolites are 4.28 billion years old, 200 million years older than any other rocks so far discovered. They are the closest anyone has come to finding Earth's original crust.
These are the oldest rocks in the world, and it's amazing when you stand on it. You can try to imagine yourself almost 4.3 billion years ago when the Earth was so young and just barely forming. Walking on this landscape. And it's a really amazing feeling.
These rocks are now yielding clues about the thickness of the early crust. O'Neill has found unusual minerals which can only form in conditions of very high temperature and pressure. They prove that the amphibolites were made at least 12 miles down in the crust of the Earth. This means that more than 4 billion years ago, Earth had a solid crust at least 12 miles thick. And a crust that thick suggests there must have been continents. And there's more. Evidence hidden in the amphibolites reveals that these rocks must have originally formed deep underwater.
Well, you have to understand that when rocks form, they can record their chemical signature. And depending on where the rocks are formed, in what geological context they will be formed, they will carry that specific chemical signature.
The chemical signature of the amphibolites is unique. It proves that when these rocks formed, Earth had not only a solid crust, but oceans.
The signature we see here, it really looks like an oceanic floor. That means there was an ocean and a lot of water already at 4.28 billion years old. So it totally changes our view of what the Earth was like before.
To the scientific world, this idea is dynamite. But O'Neill is not on his own. there is more evidence to back up his claim. In the same ancient rock sequence, geologists find another unexpected rock type called banded iron formations. These rocks are made up of alternating light layers of silica and dark bands full of a mineral called magnetite, which, as the name suggests, are rich in iron.
We usually use a magnet to try to find these minerals. It's a quick and easy way to identify for sure those rocks as banded iron formation.
Magnetite in banded iron formations only forms underwater. So these rocks are further evidence that there were oceans on Earth more than 4 billion years ago. But scientists don't know how much of Earth's surface was covered by water.
The only way to form this magnetite is to be like in an ocean. We don't know exactly what was the ocean at that time, but we know for sure that we need water to form those rocks.
These discoveries are forcing geologists to rethink their ideas of what conditions were like on Earth less than 300 million years after the planet formed.
People often think of this earlier like a ball of fire, a molten rock, but this is not the picture that we see here. We see that already at 4.28 billion years old, we probably had an ocean. We had continent that really looks like what we know today. So it changes totally our view of the early Earth.
The investigation has now revealed when the Earth's continents and oceans began to form. Evidence from amphibolite rocks at Porpoise Cove confirms that the Earth had developed a thick, solid crust 4.28 billion years ago. Banded iron formations in the same rocks show that there were oceans on Earth's surface at the same time. All of which raises another mystery. If oceans existed more than 4 billion years ago, the investigation needs to figure out where all the water came from. After its formation from the solar dust cloud 4.5 billion years ago, Earth was a fiery ball of molten rock. But 200 million years later, the first oceans were already forming. And Earth today is the blue planet, with 70% of its surface covered by water. The investigation now looks at the mystery of the origin of Earth's water.
One of the important questions I've always thought about is, where did all of this come from? All of this water, all the water in the oceans and in the atmosphere, in our bodies, in the ground. When you look at the Earth from space, what really impresses you is the water, how beautiful this planet is. Why does Earth have all this water? And how did it get here?
The question has puzzled geologists for years. Now, they believe the answer lies in space. New evidence showing how our water arrived on Earth has emerged from a meteorite that fell in 1998, but which has only recently been analyzed.
We found an astonishing thing. This meteorite contains grains of table salt, just like you put in on your fish and chips.
The clue is trapped inside the crystals of salt and revealed under the microscope. Minute droplets of liquid water.
On the computer screen you can see a little fluid inclusion, a little drop of water, and you'll know it's water. We know it's liquid because you see a little bubble moving around inside of this little droplet of water.
The amazing thing about this discovery is the age of the water.
You can date this by several different dating techniques. The salt itself is 4.5 billion years old. The water inside has to be at least that old, if not even older. There's no question about it. And so this water is at least as old as the solar system.
Here is visible evidence that water existed in space when the Earth first formed. And Zelensky is convinced that meteorites then brought the water to Earth.
And so it's looking more and more like the water arrived drop by drop in rocks like this meteorite here, landing over the course of billions of years. You have lots of material coming in every day and smacking into the Earth and depositing a little bit of water, a few drops at a time.
The scale of the meteorite bombardment needed to fill the oceans with water is almost impossible to comprehend. But scientists believe that over billions of years, there were easily enough meteorites crashing into the Earth to account for all the water on the planet.
Gradually, those rocks are sweating water, building up first shallow seas here and there that grow to be giant oceans. So you go from this to this.
Once Earth had land masses and water, the stage was set for the development of life. The next phase in the evolution of the Earth. Life is an essential element in Earth's geology. Without life, sedimentary rocks like chalk and limestone would not exist. Without life, there would be no coal, oil, or gas. Life has shaped the Earth in profound ways. But finding the origin of life has challenged scientists for hundreds of years. Now there's a new explanation. It comes from evidence found at Allende in the desert landscape of northern Mexico. At about 1 a.m. on February 8, 1969, night suddenly turned into day.
A large fireball was seen travelling from the south northwards over northern Mexico. And this big flash and this fireball was caused by a really large meteorite. It was probably about the size of a car, and it entered the top of the Earth's atmosphere at about 36,000 miles an hour.
As it plunged through the atmosphere, the meteorite broke up into thousands of fragments.
There was no crater left by the Allende meteorite, so it fell as a shower of stones, the largest of which was reported to be about the size of a beach ball. The stones are found in, we call it a strewn field, and it's an area about 30 miles by 5 miles wide, and we're here right in the middle of that strewn field.
Because the meteorite fragmented into so many pieces, geologists had to search a huge area to find samples.
Now, I actually have a smaller one of the stones here. You can see it's about the size of a plum. It's one of the most primitive type of meteorites. This means that since it formed at the very earliest stages of solar system formation, really not much has happened to it.
When they analyzed samples from Allende, geologists made a groundbreaking discovery. The meteorite contained tiny amounts of chemicals called amino acids.
Amino acids are terribly important constituents of things like proteins, and amino acids really are sort of like the chemical building blocks for life. So to find these amino acids, these molecules, within the meteorite was a really exciting discovery.
Every living thing on Earth, plant or animal, contains amino acids, and life could not exist without them. Until they were found in the Allende meteorite, scientists believed that amino acids were first made by chemical reactions on the surface of the Earth.
People thought that maybe life had started on Earth in these sorts of warm pools, maybe, a few 100 million years after Earth actually formed, or possibly through lightning causing chemical reactions in the early atmosphere. There was a few theories as to how life may have started on Earth prior to the discovery of amino acids in meteorites.
Since Allende, amino acids have been found in hundreds of other meteorites. Their discovery has revolutionized ideas about the origin of life on Earth. Scientists now believe that the building blocks of life originally came from space. Meteorites containing amino acids have bombarded Earth ever since the planet formed, and it was these amino acids which were the starting point for all life. Hunting for the origin of Earth's water and life, the investigation has revealed that the water on Earth arrived here inside meteorites. And meteorites also brought amino acids, the building blocks of life, to Earth from space. Scientists now need one more piece of the puzzle to explain the final stage in Earth's journey. From particles in the solar dust cloud to a planet where life itself builds Earth's geological features. 4.5 billion years ago, Earth formed out of the solar dust cloud. 200 million years later, the first continents and oceans were developing. Meteorites brought water and amino acids, the building blocks of life, to the surface of the planet. The investigation now moves forward to the period 3.5 billion years ago. New forms of life were about to emerge, which by their very existence would create new kinds of rocks. But life as we know it needs oxygen, and 3.5 billion years ago there was no oxygen on Earth. At the time, the atmosphere was deadly poisonous. Volcanic eruptions filled the air with a choking mixture of sulfur, methane, carbon dioxide, and sulfuric acid. But primitive life forms did exist. The fossilized remains of strange coral-like structures have been found in rocks more than 3 billion years old in many parts of the world. They are called stromatolites, and they are a clue as to how the atmosphere filled with oxygen. Living stromatolites are incredibly rare. One of the few places on Earth where they can be found is in another part of the northern Mexican desert. This is the high valley of Cuatro Ciénegas.
You might think that this is just any old desert, but it's not. This is a very special place because of particular way the chemistry is in this valley. It's unlike any other place on the planet.
The pool is like a time capsule laboratory. By examining the modern stromatolites, scientists can work out how they were made more than 3 billion years ago.
What's interesting about Cuatro Ciénegas is that this is almost like a proxy to right before the world had a lot of oxygen in it. And the place was dominated, our Earth was dominated by microbial life.
Seifert has discovered that the stromatolites are made by billions of microbes called cyanobacteria.
These right here are the stromatolites that are here at Cuatro Ciénegas. I have a piece of it here, and if you can see this blue-green rim right here, this is millions and millions of cyanobacteria.
These bacteria were to change the course of Earth history because of one unique feature. They produce oxygen.
Here at this pond, we can actually see them doing their job. We can see them making that oxygen. So when I get in the water and I actually go up to one of these cyanobacterial mats, if I look very closely, all of the community is making oxygen. And as that oxygen collects in that mat, it produces a little air bubble. And you can watch that air bubble just transfer to the top. And that's actually when oxygen is being released to the atmosphere.
$3.5 billion years ago, oxygen was deadly poisonous to other early life forms, which used sulfur to obtain energy.
Cyanobacteria developed a little molecular machine that could actually take sunlight and take water, and they made a byproduct that was oxygen. Well, on this planet back then, none of the life was used to oxygen. And it's at that point in life's history when they began making excess oxygen that got into the atmosphere, our whole world changed in the way it worked.
Over geological time, there were enough cyanobacteria to produce trillions of tons of oxygen. creating the atmosphere we breathe today. And they were responsible for changing the way all life evolved.
From an evolutionary standpoint on planet Earth, we are where we are because of cyanobacteria and the fact that they managed to fill our atmosphere full of oxygen. Because unless we'd had that gas, we wouldn't have the complex organisms that we have on the planet. You and I wouldn't be here today.
Once the atmosphere began filling with oxygen, the stage was set for the evolution of all plant and animal life. The impact on Earth's geology was profound. Over hundreds of millions of years, decaying plant matter from tropical forests built up compressed layers, which eventually formed all the coal, oil, and gas deposits on the planet. Sedimentary rocks like limestone and chalk are made largely from the skeletons of marine animals which accumulated at the bottom of shallow seas. Without life, Earth's geology would be very different. The investigation into the birth of the Earth has uncovered evidence revealing the secrets of Earth's development. Experiments on salt crystals in space reveal that the Earth began to form when mineral grains in the solar dust clouds stuck together. Evidence from meteorites proves that Earth first formed 4.567 billion years ago. The oldest rocks in the world are evidence that continents and oceans were forming 4.28 billion years ago, much earlier than previously thought. Liquid water in meteorites proves that water was brought to Earth during billions of years of meteorite bombardment. 3.5 billion years ago, a billion years after it first began to grow out of the solar dust cloud, Earth had continents, oceans, primitive life forms, and oxygen. The birth of the Earth was complete. A new canvas on which billions of years of geological processes could mold the planet we inhabit today.